So our topic for today is the last little bit of information that we don't know how to figure out, which is our rate laws. So if you remember the very first time we discussed rate laws, I had mentioned there's no way to guess what this rate law is without actually doing an experiment to verify whether or not that's the actual rate law. So we're going to talk about what those experiments look like and how we analyze the data to try to figure out what the actual rate law is. There's two forms that we're going to use, which are up here. We'll get to both of those in a minute. This is all in Fogler Chapter 5. There's a lot more information in Chapter 5 than we're going to cover here. What we covered today should be enough for problem 7.4 on the homework, but you might need to wait until the video lecture if you're not sure how to do the actual calculations that we're about to do. You may have done them in a previous class. If you know how to do linear regression and get some numbers out of that, you might already be familiar with this. We've done linear regression on other homeworks. This is going to be similar. And then just a reminder, we've got our third exam on Wednesday. It'll be up to and including that discussion we had on multiple steady states, which I looked back in the lectures. I think it was lecture 18. So anything that came after that is not going to be on the exam, but up to and including multiple steady states could be on the exam. So our procedure for determining R sub A, if we needed to do this in some actual setting where we really needed to know what these values are, comes in 3 steps. And these 3 steps might not be done all at once, right? You might have to loop through them a few times as you learn more and more about your system. These procedures are the same ones anytime you see an actual rate constant for a reaction. There was probably a paper published somewhere where they figured out the rate constant for that particular reaction. That's about the only way that we know what these rates are. So the first step, and I'm going to give each one of these steps about 1 slide, is to simply guess R sub A. We have some techniques that we can use to make a good first guess for R sub A, something that at least has some sort of theory behind it that gives us a way to get close. 4 of those theories are as follows. One of them is what's called an active intermediate. So this is if you have taken like an OGEM class or maybe even a PChem class, sometimes you'll see a radical species or something that's somehow activated such that it will react very quickly. Usually active intermediate theories result in rate laws that look something like power laws, so K C sub A to some power, or some combination of those. There's a pretty good discussion of active intermediates all through Chapter 7 of Fogler. So we're not going to cover Chapter 7, but this is one of the reasons why Elements is nice compared to Essentials of Chemical Reaction Engineering, because you get an entire chapter on some of these theories. So these are just places to go if you at some point need to come up with one of these. There's another version called Kinetic Theory, which we're not actually going to get into in week 10. That was one of the options where we would have seen this, but we're not going to. Kinetic theory tends to result in power laws as well. Something like that. Fogler has a nice discussion of kinetic theory as well, but it's in the appendix, which actually I think is the CD-ROM, in R3.1. Kinetic theory and the active intermediate theory are actually somewhat related. It's just that active intermediate suggests an extra type of species inside kinetic theory. Then one where if you go to your grad class, you'll learn a lot about solid catalysis, catalysts, or catalysis. These are rate laws that look like the ones that you see on the project. So where there are multiple and different types of equilibrium coefficients, those usually come from catalysts because you're talking about multiple procedures. So I've briefly mentioned along the way, things like the molecule has to diffuse down and then it has to attach to the surface and react and come off the surface and then diffuse away. When you account for all of those, you end up with those rate laws like you would see on either one of the projects. Specifically the blue project, you can see quite a few more of those. The green project, not so much. Fogler again has a big discussion of solid catalysis. It's several chapters, but the primary chapter is 10. And then the last big form that we usually get is something like either a substrate or enzyme kinetic mechanism. This is pretty much any time you go into a bioreactor, you're probably going to use an enzyme and a substrate. Substrate is usually a reactant, enzyme is a catalyst, but they have specialized terminology because they develop theirs separately from us. If you, again, check out your book, there's a pretty good discussion of this in Chapter 7. So the point here is not you need to figure out what all of those mechanisms are, it's that there are many different ways to try to figure it out. These capture most of the ones that we encounter on a regular basis. They're not the only ones, but they cover almost everything. Each one of these on their own have entire journals dedicated to them. There are, I'm sure, people who have done PhDs on each process. You can undoubtedly find books on each one of these topics. So you can go into quite a bit of depth. Obviously, this is about as deep as we're going to go into each one of those, because the only form that we're going to use is a power law form. Because with a power law form, you get a lot of the same behavior, which is usually some sort of a rate is proportional to a rate constant and a concentration raised to some power. So I'm using alpha as an arbitrary power. And at this point, we don't really care whether or not the reaction is elementary or not. The stoichiometry can be whatever we want, and we're just going to have this arbitrary alpha up there, because most reactions don't behave in an elementary form. They might look like they do under certain conditions, but when we're just getting started, we probably don't know what that order is. These methods up here on the top can give us an idea of what that order might be, but you still have to run through the experiment and figure out whether or not that order is appropriate. Yeah?
Do you assume that alpha is an integer or any number?
Any number right now.
Okay.
Yeah.
Oh, which grad class is the solid catalysis about?
That is our grad CRE class. Chemical reaction.
Which number? Do you know? I'll be right.
252, says Jenna. Are you in? No, you already took that.
That was in the winter. Yeah.
That was in the winter. So we're always going to assume some form of a power law down here. It makes the math a little bit easier, and you can get through the rest of the steps and get an idea of what you would do with more complicated power laws after that. So your first step is go to one of these theories and figure out what do you think the rate law should look like. The next step is the one where, again, there are books published on this. There are classes, multiple classes dedicated to it, because it's not easy to do. Which is to run a, this is the key word, well-designed experiment. Well-designed is pretty hard to do. There's a lot of ongoing research on how to better design these sorts of things, mostly in the form of, can I make a better reactor to measure what I want a little bit more easily than I might otherwise do. There are at least two normal ways. Oh, sorry, there's a really good book on this too. That book is called, I'm going to abbreviate the crap out of this, Experimental Methods in Catalysis Research. Or sorry, Experimental Methods for Catalysis Research. It's an entire book dedicated to just one aspect of this, which is how do I design a good experiment if my method follows some sort of catalytic mechanism. You don't have to read that book, but it's an indicator of how deep you can go into each one of these subjects, depending on what you're trying to accomplish. Usually these will take place in one of three reactors. So the easy one is the batch reactor. So a batch reactor, as we saw before, is just a batch, and what you end up calculating for something like this is a plot of concentration versus time. Right, so you have to come up with some way to measure whatever it is that you're interested in, and you maybe take little samples, or you have an online measurement to keep running it over and over and over again. You'll do an experiment like this when you get to 176B. We have a photocatalytic degradation process, and you'll figure out the rate law by doing exactly that, which is dump it in there, turn the light on, add the catalyst, and watch the composition decay. The experiment is going to give you this CA value. So for all of these discussions, you know what CA is because you have gone out and run an experiment on it. This is not something that we have to determine for any of these methods that we're going to talk about in step 3. You know what CA is. You have gone out and you've run a measurement and you've taken little data points at various times and figured out what CA is, which is a little different from what we've been doing in every step up till now, which was we needed to figure out what CA is. Now, presumably, we know what it is because we can measure it. Another common type of reactor is called a differential reactor. This is the kind of reactor that was used to get the kinetics on your blue project. So a differential reactor is a style of packed bed reactor. So here's our tube for a packed bed reactor. The reason it's called differential is because it only has a very, very tiny amount of catalyst in it. So I will draw a single row of catalysts as black circles here. The rest of it is just empty support, or sorry, inert support that's only there to basically hold the catalyst in place. But it's not actually reacting anything, it's just inert. And so there's a very tiny amount, delta W, of catalyst. The reason that that's nice is because it's such a tiny amount of catalyst that we basically treat the whole thing as an isothermal CSTR for that little tiny chunk. And the math ends up looking pretty good. We end up getting something like the rate laws are just proportional to the amount of product that we make divided by the amount of catalyst that we have, Ra prime. So if you have a gas phase catalytic reaction that's catalyzed by some sort of a solid, you'll typically see a differential reactor, which is just this. They're also really easy to make because they don't require a lot of catalyst, so if your catalyst is really expensive, you don't need particularly much of it to do something like that. Again, that's the one that your projects used to figure that out. And then all the other ones are just various flow reactors. If you can't use one of these generic ones, you've probably got a special one, which was designed specifically for your system. If you want to see a couple of examples, your book has a nice summary table in sections 5.7.2 to 0.3. There's all kinds of things like special CSTRs that are designed for mixing up solid catalysts or something like that, or fluidized beds, which keep the catalyst moving around in the fluid, things with recycle, things with different kinds of heat exchangers, all of which are generally designed for a particular application. These two, the batch and the differential, are the ones that are kind of generic. You can do a lot of different rate analysis with those two reactors. The only one that we're going to deal with is the batch reactor. There's plenty of discussion about differential reactors. If someday you get bored and are feeling somewhat masochistic, you can go and learn more about differential reactors because they are pretty useful. It's just we don't have enough time to go into a lot of detail. It also helps to take something like the grad class where you know a little bit more about the processes that go on in solid catalysis so that you can describe what those rate laws should look like. So this is a step that we have to have a lab for. There is no way to get around this. You can't use any level of theory that we know of right now to actually do anything like this, so you have to get into a lab and do it. Obviously, you don't have to get into a lab for this class, so you will always be given this information. There'll be a table of concentration versus time or something like that, which represents what you would have gotten if you went out and did a well-designed experiment. We just don't have time to shove another class into 2 weeks, so we're just going to give you that data. Step 3 is the one where you'll spend most of your time in terms of analysis, which is the part that you would probably expect, which is to check your model versus your experiment. If your model doesn't match the experiment, then your model is wrong, and you have to go pick another model. Usually we can get pretty close if we use one of those methods in step 1 that is applicable to whatever system we're dealing with. But nevertheless, you need to go out and do the measurement and then check the model versus experiment. There were 3 models proposed in the paper that developed the kinetics for your blue project. They had to go through and figure out that these models don't work and this one does. And then even the one that they did that had like 14 or 15 steps in it, they cut out about 6 of them because they said they weren't important. So there's no way to know from any of those theories which one is right until you check it versus experiment. There are lots of different ways that you can check things versus experiment. And just like step 2, there's about 3 that are of interest. Step 1 is to do what's called a differential analysis. So differential analysis says that we're going to take the material balance, we're going to combine it with our rate law, but then we are not going to integrate. Given that I said we're not going to integrate, you can probably guess what we're going to do on the next step, on the other version, which is to integrate. Basically what this says is if we have something like dCA dt, let's say we have a first order power law, and so we get something like minus k times Ca. That's all the further we're going to take that. We're not going to try to actually integrate that, even though we could. And instead, what we're going to do is create a plot where we have Ca on the x-axis. So this is our x parameter. And then we could have something like minus dCA dt on the y-axis. So I'll make that one blue. Presumably, if we plot minus dCA versus, or dCA dt versus Ca, we should get a straight line of data points where the slope of this line is equal to k. There are many different ways that you can figure out from a tabulated value of Ca versus time to approximate something like dCA dt. We saw actually a method of that in the lecture that I gave on how ODE 45 works in terms of numerically solving a differential equation. It's something similar, which is you take the deltas between any 2 data points and you have a way to approximate what dCA dt is. There are lots of different ways to do that. You can see them all in Fogler if you want. The other version is related to that, which is the integral method, which is to take your material balance, combine it with your rate law, R sub A, and you integrate. So for this same sort of a rate law that we had up here, if we wanted to take that same rate law and figure out what it looks like for an integral analysis, we would actually integrate that thing. Presumably we know where the initial concentration was, and so we can integrate this to get something like C sub A is equal to Ca naught e to the minus kt. An important step that we're going to learn about more here in a minute is to take that equation and linearize it. There are several tricks we can do to linearize something, such that this equation looks more like natural log of Ca over Ca naught is equal to minus kt. And so again, we could look at now a plot of time versus minus natural log Ca over Ca naught, and this should again be a straight line. And here the slope is k. So our value for x and y, what we're putting on the x and y axis, looks a little bit different for each one of these. But they're only there to make our lives easier in terms of the statistics that we need. But these are the general two methods that you can do. If you can actually integrate the thing and get a closed form solution to whatever your rate law is, you can do something like the integral approach. The integral approach is the only one that we're going to deal with. The differential approach is a little bit more flexible because you never have to actually do an integral. All you need to do is write down the rate law, and you've more or less got all of the math that you need at that point. So there was no calculus with a differential analysis. It's a little bit more tedious to do, which is why we're not going to do it. If the rate laws are straightforward like a power law, then you can get away with something like an integral method where we can actually integrate the material balance and get a plot like what we've got over here. The third methods, which I'm not going to bring up, but if you, that's not true, I'm going to bring them up right now. We're just not going to go into detail with them. If you check out Fogler 5, 3, and 4, 5.3 and 5.4, I'll put fog around Fogler. These are the specialized methods where if there's some limitation you have on your reactor and you can't run it for very long, so you have to make a special type of analysis, you can do that. There's a method called excess reactants where you dump a bunch of one reactant and very, very little of another reactant to figure out complicated rate law. If things go really fast, you can use methods of half-lives where you just measure the half-life of stuff, all of which are a little bit more specialized. They generally follow a similar analysis here, which is I need concentration versus time data in order to figure something out. The only one that we're going to use is the integral method because we can actually evaluate most of these integrals analytically. There's something similar about both of these plots, which is they both assume that a plot will give a straight line if you've got the right mechanism. If your actual data looks something like this, right, so kind of curvy like that, that's not a very straight line. That doesn't mean there's something wrong with your data. It means that the rate law that you've assumed is not the right rate law for that system. And that's exactly how we evaluate whether or not these things are good fits or not, is does my data look like a straight line when I plot it on special axes? So the choice of that special axis changes depending on what your rate law was. We saw two examples here where if I plot dCA dt versus CA, I expect a straight line. Or down here, if I plot minus ln CA over CA naught versus T, I expect a straight line. So how do we come up with a method like that? You need the equation, and then you need to understand that what we are trying to do is get this equation, which is y is equal to mx plus b. This is sort of our golden equation for all of these. If we can force anything into a linear form, this being a linear form, if you've never heard that, I don't know, most of you have probably heard linear forms before. These are the ideal way to go. If you can force your data into a linear form, because it has several advantages. The first advantage is that there's only one answer. So it doesn't matter exactly how you get it into that linear form, you will always get the same value for your coefficients, which is nice. Part of the reason why that there is only one answer is because that there is no guessing involved. If you have a set of data and you have an equation, you dump it into a certain set of statistical analysis tools, you crank the wheel, and you always end up with the same answer. It doesn't matter if 20 different people do it, they all have to get the same answer because nobody can start from a different location. In a linear type of form like this, there's only one answer because nobody has to guess anything, so nobody can guess anything different. The third reason that this is a really useful technique is because it can be done by eye. What I mean by eye is that i.e., if you are given a plot, it's pretty easy to calculate a slope and an intercept if the line is straight. It's a lot more difficult to do the next method that we'll talk about in a moment. But if I give you a plot and I put the axes as something relatively easy so that the lines line up, it's pretty easy to figure these things out by eye. The general procedure then that we have, if we want to know a rate law, so e.g. what you would do on your homework, step one is to guess RA, which I will probably give you what RA is. Step two will be to integrate the material balance. With this R sub A that you've got. And then step three is to rearrange to a linear form. So linear form is sort of a catch-all because I don't know what those forms will look at until I actually integrate them. But generally that linear form will be something that looks like y is equal to mx plus b. Generally, each rate law that you come up with is going to have something different for the x value, something different that you put on the x-axis, and something different that you put on the y-axis. And it's up to you to figure out how do I have to rearrange this equation in order to get it to a form like that. There are some variations where your linear form might be different from somebody else's linear form, but the nice thing about linear regression is you have to get the same answer as long as you were both mathematically correct in your forms. So let's take a look at an example of what we mean here. And in fact, you'll have to do exactly this example on your homework. If we say minus R sub A is KCA squared. Let's assume that our form follows a second order power law form. So that was step one, right? We guessed it in the sense that we were given what that equation is. Step two would be to solve the material balance. So dCA dt is going to be equal to minus KCA squared. If I integrate that, I get 1 over Ca minus 1 over Ca0, Ca0 being the initial condition, is equal to Kt. So is that a linear form?
Not yet.
Not yet. Why not?
Because we have 1 over y, essentially. We would have to find the inverse of Ca if we want that to be our y value. Or we can just call 1 over Ca our y value.
We could just call 1 over Ca our y value, right? We can call anything that we want our y value. So there's actually two different ways that we could do this one. We could call this entire parameter y. All right, so when I go to calculate my the values that I'm going to put on my y-axis, those values aren't going to be Ca. Those values are going to be 1 over Ca minus 1 over Ca naught. My x value is going to be t. So I'll have y is equal to something m times x. So here my slope is expected to be t. What's my intercept? Should be 0 in a system like this. There's an imaginary plus 0 over here. So this is plus b. So the plot that I would create for something like this, up here on my y-axis, is going to be that entire value, 1 over Ca minus 1 over Ca naught. And my x coordinate down here is time. If I were to do something like that and my data actually fit that particular form, I would end up with a straight line that goes through 0 and a slope of k. But that may or may not be what our data look like, right? That if our model is representative of the true rate law, we will get something like this. But it may also be the case that our data looks something like this. So if we plot 1 over Ca minus 1 over Ca naught versus t, and we don't have a straight line through there, that means that's not the correct rate law. It doesn't mean that there's anything wrong with what you did, it just means your experimental kinetics don't behave like the rate law that you've assumed. But it doesn't necessarily mean that anything is wrong. An alternate way to do this exact same one that you will see used semi-often is 1 over Ca is equal to Kt plus 1 over Ca naught. But this one still looks similar in the sense that we've got a y over here, an x here, and an m here. And now our b parameter is something like this. So these two forms aren't the same form, but the nice thing is if you do the math correctly, you will get exactly the same answer for k, regardless of which of those two forms you use. If I were to plot this one, I'll just briefly sketch in the plot down here. If I put a t here, my y value would be 1 over Ca. So again, we would expect a straight line for that. Either one of these, actually. We would expect a straight line if our experiment actually followed that form. And so what you're going to do on your homework is imagine if it's not Ca, maybe it'll be K, maybe it'll be KCA, maybe it'll be KCA squared. You can imagine all the various permutations that you can get from something like that. So just plain old guessing the power law will end up, or guessing the rate law without anything behind it, with no theory behind it, is pretty unlikely to give you the right answer. Or if it is, it's because you did an awful lot of work doing one of these analyses for every single combination of what you could have for a rate law. So these are the three that you're going to focus on in the homework. You're going to do something just like this where you integrate the material balance, you rearrange that equation somehow so that it looks like it has a linear form, and then you'll plot that linear form and figure out if it's a straight line. The tools to do that, if you're not comfortable doing that in whatever piece of software you have, are the topic of the next lecture, which is the video lecture. So all of this can be done within the same GUI inside MATLAB. So it does all the plotting for you automatically, which is pretty nice. It makes life a little bit easier. How do I figure out which one of these, if I have K or KCA or KCA squared, how do I determine which one is the actual fit? I need some sort of a parameter that will tell me whether or not the one that I have is the best one. Sure, if you want to answer that. I was about to answer it, but go ahead.
R squared.
R squared is probably the one that you see most often. R squared is not bad if you're comparing everything on a linear basis. R squared gets a little bit more funky if you're not doing something that's on a line. So whenever you take your statistics class for chemical engineering, what's that one? 114. You'll learn a better suite of skills to actually evaluate whether or not one is better than the other. But for the most part, for the level of detail we're getting into, R squared is pretty good. There's not too much wrong with R squared. Just as a reminder, R squared is something that you can calculate, but it's almost always provided automatically by any of the software you use, including MATLAB. So your R squared value is something that's limited to 0 and 1, with 1 being the best. 1 says exactly all of your data points are represented by whatever equation that you have. Your line goes right through all of your data points. It's pretty hard to get an R squared of 1 unless somebody is fudging your data to make it come out as a 1 in one particular case. The value of R squared that is quote-unquote good enough varies from discipline to discipline. If you go over to like a bio and they see an R squared of something like 0.6 or 0.7, that's probably pretty good, because bio experiments are really hard to do. If you go more in like classical chemical engineering, then R squared has to be more like 9.8 or 9.9, or sometimes even more than that. So it depends on where you're going to decide which one is acceptable for an R squared to say, yes, this model does match our data. But for the experiment, or for the examples that we're doing, whichever one has the higher R squared value is the one that we assume is the one that matches our data set. So we're aiming for one that has an R squared value. Where that r squared comes out, again, that's the topic of the next lecture where I'll show you how to do that inside MATLAB. You don't have to do any calculations for r squared, it just pops up, unless you're doing it by hand, in which case, then you do. These are all great if you can make a linear form for your rate law. An awful lot of rate laws don't have a linear form after you integrate your material balance. For example, the last one that you're going to have to do in your homework is if your rate law is kCa raised to an unknown power alpha. So alpha is another unknown that you are going to ask your data to provide to you. You're going to do some sort of a statistical analysis to figure out what is the best combination of k and alpha to reproduce my data. So there are two unknowns here. The first unknown parameter is k, the second unknown parameter is alpha. So we don't know those, they're going to come out of our analysis. Alpha can be almost anything that you want. The way that we're going to derive this makes an assumption on alpha, but that'll be a little bit more obvious when we see it. If you integrate the material balance for this, you get the following expression for Ca. It's always bad when he starts with a bracket. Ca naught raised to the 1 minus alpha minus a parentheses with 1 minus alpha inside it times kt, and then everything inside that bracket raised to the power of 1 over 1 minus alpha. What can alpha not be in that equation? 1. If alpha is 1, you'll just have to do it by hand, which is the one that we had already shown on a couple of previous slides. The problem with this equation is that there is no linear form for that equation, so we're stuck. We can't use the linear regression tools that we saw before, so we have to use a different set of tools called nonlinear regression. The principle behind nonlinear regression is fairly straightforward. We're going to take the actual parameters that we are interested in. So presumably we've got a data set of concentration of A versus time. And I'm going to put those in there as black circles. So the black circles that we have are the concentration of A. I'm going to subscript this with measured, comma m. That's the value that we actually went out to the lab and got from our experimental system. I would hope that we would have more than 3, but we're just going to use 3 as an example here. The next set of data that we're going to put on here, which I will do with red circles, is the concentration of A that we get if we calculate A. So the subscript C here means that we calculated it. In order to calculate something, we have to guess K and alpha. If we can make a guess for K and alpha, just pick 2 numbers, 0.1 and 3 or something like that, then you can calculate Ca based on this equation up here. So this Ca that we wrote up here is C sub A comma C. It's the one that we calculate. If we calculate something like that, what we'll find is your first guess was probably pretty awful. And so if you put your data points on here, maybe they look something like this. Evidently, C sub A that we measured is not the same as C sub A calculated for a particular guess of K and alpha. So then our question is, we need to make a better guess. How do we make a better guess? We let MATLAB make a better guess. We're not particularly interested in that mechanism. However, if you took at least CENG 15 with me, it might have come up in the other ones. If you remember the f0 function or the fsolve function, those iterative methods that we learned about in there are the same kinds of iterative methods that are being used here. But they happen behind the scenes so that we don't have to do it. We should have some kind of an understanding of what is being optimized here. Generally what we want is for those 2 dots to be right on top of each other. So we can calculate the differences here between each one of those dots. So if I calculate C sub A measured, and I compare that to C sub A calculated, and then I sum those up over all of my data points. Right? I have multiple data points, so I need to know the difference between all of those data points. If I do that, and I keep guessing k and alpha until that sum is minimized, then I have the best guess. When it's minimized, well, I'll draw another plot for what it looks like when it's minimized. Before I show that plot, the disadvantage of just calculating the difference between a measured and a calculated value is what? Can anybody see what that difference is? That problem is?
What was the question again?
The question is, what's wrong with this equation? If I just want to minimize this sum, there's a cheating way to do it.
Would you need to take the absolute value?
You would need to do that. Why?
Well, the difference between like the first data point, let's say it's positive, that means that the last data point is going to be a negative value.
Yes, so just by sheer coincidence, you can get that sum to be equal to 0 if, for example, this difference up here, the first one, happens to be the same as this difference over here because one's positive and one's negative. So the fit can be absolute crap and yet still look like it's really, really good just because they happen to deviate in exactly the opposite directions. We don't want that. That's not a real effect. So there's one of two ways. You can either take the absolute value of that term so that all those differences add up in a positive way. The statistical convention that we use is to calculate that value squared, which ends up doing the same thing, right? It always makes sure that that's a positive. This particular sum has a name. The symbol is s squared that we usually use. If you take a statistics class, this is approximately what looks like the sum of squares total. I think there's an extra name and extra parameter of n somewhere in there for sum of squares total. Actually, no, I think that is the sum of squares total. So if we can make this value, if you can make either s squared, or if you're a statistician, if you make SST as small as possible, then you've got the best combination of k and alpha for something like that. So a really good combination then would look something, I'm just going to reproduce that plot over here. So if I've got T here and CA over here, and I've got my measured values again like this, a really good combination of K and alpha will put those dots pretty much right on top of each other. They will probably not be directly on top of the data points, even if that method matches whatever true rate law you have. They usually will not get exactly on top of each other. If they are ever exactly on top of each other, again, r squared will be exactly equal to 1. That's for the case where this will only work if you have a movie, because if you have a black dot and then you find out that the red dot is exactly on top of it, that's when r squared is equal to 1, if that's true for every one of those points. That's usually not the case. We usually get in the high 90s, though, for most of the data that we deal with. This is what's called nonlinear regression. The reason it's called nonlinear is because we don't have a way to turn that equation that we started with from a material balance and a rate law into a linear form. A linear form is usually what we would call linear regression. We would apply linear regression to a linear equation. If the equation is nonlinear, then we need nonlinear regression. There's a lot of information about nonlinear regression in many, many statistics books. Fortunately, the same tool that MATLAB uses to do linear regression is the one that we can use for nonlinear regression. It also makes it very easy if we ever have to put an expression like this inside of a nonlinear regression tool. It can be kind of tricky to do. MATLAB lets us do that just by typing in symbolically what's happening, and then it'll figure out what the best fit is in terms of nonlinear regression. So that's the other version that you're going to have to use on your homework. The first part will be assume that RA follows one of these power law forms. The other one is, what if we didn't know what that power law was? With some unknown alpha, we're going to have to do nonlinear regression to figure out what that is. That's the topic of the next video lecture, which I'm not going to wait until Friday to post that. As soon as I have that lecture done, I will post it so that you can finish up your homework. On the other hand, if you already know how to do linear regression, you can tackle an awful lot of problem 4. And certainly if you already know nonlinear regression, you can finish the rest of problem 4. So, no class on Monday, exam on Wednesday, no class on Friday. There's a video lecture for Friday, so you only have to show up once next week. And then in week 10, we'll have Dr. Fenning on Monday and 2 review sessions on Wednesday and Friday. And that'll be it. So the next time I will see you is Wednesday. Enjoy your long break. Come back ready to go for another exam. Thank you all very much.